K prime, double prime?
No, just
K prime of 2?
if K of X equals F of X to the negative 1. And I think that there's a graph to it, so you want to
What, do you know what page we're on?
150, like around 160.
160.
Yeah, there's a graph to it
Okay.
on 161.
Okay. So K prime of 2 K of X is to the negative 1. Okay. So we have on this graph, it looks like we've got 2.5 is our point, or 2 comma 5 rather. And then we know there's got the point 2.1 and 5.3. So you've got a tangent line going through here. And then we have a point on the tangent line that's supposed to help us somehow. That's 2.1, 5.3. So first let's see if we can do our derivative. So we've got K prime of X. So this is a function raised to the negative 1 power. So it's a chain rule derivative. So we're going to go negative 1 times our function to the negative 2, you with me? Times the derivative of the inside function, which we're going to call f prime of x. Is that okay? And now we're going to evaluate that at 2. So k prime of 2 is going to be, well, let's go f prime of 2. And that's going to be a negative out here. And this is going to be f of 2 squared. We okay so far? Now, the tricky part is evaluating this f prime of 2. So remember, f prime of 2, that's why they're giving us this tangent line. The f prime of 2 is the slope of the tangent line. And because we have 2 points on the tangent line, we can figure out the slope from that. So the slope of the tangent line is going to be y2 minus y1 over x2 minus x1. See where I'm getting that from? So that looks like 0.3 over 0.1, and that's just going to be 3. So that's our slope of the tangent line, which is going to be our derivative evaluated at 2. So that's going to be a negative 3. F of 2 is going to be the 5, because this point is on the curve. So that means f of 2 is equal to 5. You okay with that? 80. Okay. And that's going to be 5 squared. So I think we're going to get negative 3/25. Kind of crazy. There's a lot in that problem. Anything else?
Can
Okay.
we do 65?
65? Do I need the book for that? Yeah, I do. So 65. So 65 says that we're going to use the table and the fact that f of x is invertible and differentiable everywhere to find. I think hold off on this one because I'm going to talk about derivatives of inverses today. And then I think that'll make this more clear. Okay? Other questions? Okay, so before I forget, I'm going to talk about finding derivatives of an inverse today. But we're also going to do a gateway exam. So let me talk a little bit about that and give you a gateway review. Oh boy. Here so I wouldn't forget. So the idea, there's say this word that. I forget, I picked a day, but I don't remember where it is. It's on Canvas. I don't think I posted it yet. I think I picked a day next week where we're gonna take the gateway exam. So the gateway is this, as you can see on this worksheet, on this review worksheet, there's 10 derivatives. So it's just kind of where we are. I don't think I put even any inverse trig derivatives on there at this point. So these are, it's called a gateway because at this point in time, you just have to know how to do the derivative stuff we have learned. You have to know the trig derivatives. You have to know exponentials. You have to know the product rule, the quotient rule, the chain rule. And if you don't, then the rest of the class is just going to be a blur because you're not going to know if you're understanding new concepts because you're stumbling and fumbling because you don't remember what the derivative of secant is or recognize when it's a product rule versus when it's a chain rule. So it just muddles up everything going forward if we just don't have a pretty high level of mastery of this, because this is just what we are going to be working with all the time from here on out. Yes.
Is the key gonna be online?
On the back.
I believe it is.
Okay.
It's on the back of this, but I think it's online as well. So what this is, it's called a gateway exam because this is a gate that everybody must pass through to continue successfully in the class. So, and I don't remember, it's going to be some day next week. I think we're going to take this. We can look it up when I post the module for next week. But as you can see, there's just 10 derivatives. It's not going to take us a full class period. I may have even, let me just check real quick here. I'm going to pause this video. So I guess I'm aiming for Thursday and Friday next week because we have Tuesday off, so we'll have to go to school Friday anyway. So the idea is you'll have these 10 derivatives, but I will give minimal partial credit. Because what I really want to know is, can you do the right derivatives of the trig functions, of exponentials? Do you know the product rule, the quotient rule, the chain rule? So if you make an error in a derivative, there's 10 problems, there's a 100-point test. If you make an error in the derivative, it's minus 10 for that problem. Okay, if you do the derivatives correctly, and then maybe you make a little mistake or something in the simplification, I may take off a point or two. But generally, if the derivative isn't right, the whole problem is wrong. Okay, if you get less than 80%, it's a 0, because you have to get to 80% mastery of this to be successful going forward. The good news is if you don't pass at 80%, you get to take it again. And the second time you take it, the best you can get is an 80. So if you score better than 80% the second time, I'll replace that 0 out of 100 with an 80. Okay, but if you don't pass it there, it stays a 0 until you can, retake it and pass it at the 80% or better mark, at which time it'll be replaced by an 80. So it's just to emphasize that we just have to know these things, these derivatives, kind of backwards and forwards, just off the top of our head, without having to consult notes or note cards or look up what's the derivative of a secant, or is that a product rule or is that a chain rule? I'm not sure. We have to clarify all of that. Okay? So that's what this is to practice that. The test will look something like this. It's just going to be 10 derivatives. It's nothing, nothing deep conceptually, except that you just have to be able to do the derivatives. It's the doing of calculus more than the understanding part that we strive for on most tests. Okay? Okay, so let's talk about the derivative of an inverse. So this is more rolling. Thank you, Priya. Well, you missed all of that. It's always nice to be here in person. Okay, so we're going to try to tell and we'll review this a little bit, if this is a one-to-one function. So because I was late turning on the video, I'm telling you that for their benefit, we learned a new way of telling if a function is one-to-one or strictly monotonic. That's going to be if its derivative is always positive, greater than or equal to 0, or always less than or equal to 0. So is f one-to-one is our first question. And we know that to determine that, we can look at its derivative. So f prime of x is going to be what? 3x squared, good. That's 1. So now as you look at the derivative, can we tell is that always positive or always negative? Always positive, right? Because no matter what you plug in for x, when you square it is positive. Times a positive 3 is still positive, plus a positive 1 is positive. So this is going to be greater than or equal to 0, actually greater than 0, for all x. So that means f, the answer to the question is f one-to-one is yes. So that means it must have an inverse. Can we find the inverse? How do we find an inverse? Switch the x and y, solve for y, right? So we'll get x equals x equals y cubed plus y plus 1. All you have to do is solve for y. Any good ideas? See the problem? We can't solve for y there. So we know it has an inverse, but we can't find the inverse. Here's the crazy thing. We can still find the derivative of the inverse at a particular point with a little help from technology. So even though we can't actually find the inverse function, we're going to talk about how we can still find the derivative of the inverse at a particular point. Okay? So in this case, we're going to be interested in, what do I want to find? Let's find, now we got some crazy notation here. So we're talking about, we're interested in finding the derivative of the inverse. Now that isn't awkward notation. You have little tick marks all at slightly different angles, right? So that's the derivative of the inverse, and we're going to look for it at 11. That's our goal. Okay? Okay. But we're not ready to tackle that problem yet. We'll come back to that. So our goal is we're going to find the derivative of the inverse there. But first, let's do something we know how to do and get a little bit more understanding about the derivatives of inverses. I've really painted myself in a corner here since I have only one board to use. Feeling very constrained here. Okay, so let's consider, instead of a problem we can't do yet, let's consider a problem that we can do. And then I want to look at it visually, graphically, and then also algebraically. And somebody keep their eye on the clock so we don't run short of time, because that's always an issue. So let's say f of x is x cubed. Okay, now we know how to find its inverse. What's its inverse?
3x squared.
The derivative is 3x squared. We're going to need that too, but its inverse is, yeah, so can we just say cube root of x? Okay. Okay, so we know the function, we know its inverse. So we even know the graph of these. Let's put these, and we're going to keep a visual here. So x cubed is going to do something like that. And cube root is going to do something like that. Okay, so this is y equals x cubed, and this is y equals the cube root of x. Okay? Now let's look at, we know a point that's on this curve. So if we plug in 2 for x into the original function f, then its y coordinate is going to be 8. 2 cubed is 8. Now, if we take the derivative of f, that original function x cubed, its derivative is 3x squared. Ainsley knew that one. If we find the derivative at 2, that is going to be 12. Good. I was all by myself for a moment. Thank you. Okay. Now, let's see what that looks like on the graph, roughly. So at the point 2, 8, I'm going to say right there is the point 2, 8. Its slope is going to be really steep. It's a positive 12. So here is our tangent line, and its slope is going to be 12. Okay? Now, let's look at the corresponding point on the inverse. So if 2, 8 is a ordered pair, a point on the original function f, then the corresponding point on the inverse is going to be 8 comma 2, right? Because when you plug in 8, cube root of 8 is 2. So these points go together for the original function versus its inverse. Now, the derivative of the, here's my crazy notation. The derivative of the inverse, so f inverse in parentheses prime, which is really awkward. Okay, that's how we write the derivative of the inverse. Is going to be, well, this is the derivative of x to the 1/3, which is good, 1/3 x to the negative 2/3, which for evaluation purposes, we can say is 1 over. Good, and the 3 is there from the 1/3 also. Good, cube root of x squared. Okay, and if we evaluate, here's our weird notation, the inverse evaluated at its x value, which is 8, we're going to take the cube root of 8 is, square that is, times 3 is 1/12. Oh, how about that? The derivative of the original function was 12. The derivative of the inverse function at the corresponding point is its reciprocal 1/12. It's not a coincidence. Okay, so we go over here, and I didn't draw this very good, but, well, use your imagination. That's a 2, and its slope is going to be 1/12, whereas this had a slope of 12. The tangent line has a slope of 12. So my graph is sorely lacking in scale here. But the idea would be, so now you're going to have to use your visualization skills. This should be the line y equals x, where if you flipped on each other, they would land on each other. So if you flip the yellow in the pink line, it would land supposedly on the blue line, which is why when you flip it, this slope of 12 would land on the 1/12. Okay? Okay. So that's nice, but we want to be able to figure out how to do this when we can't find the inverse. Okay. Now, here's where it gets more complicated. Here's our strategy. First, this notation is really awkward. This whole derivative of an inverse is awkward, so I'm going to just say, let's say g of x is going to be f inverse of x. Now we don't have to fool with the notation, we can just think about the rest of it, okay? Now, if two functions are inverses of each other, then it must be true that f of g of x is equal to x, right? A function, f of f inverse of x is x, f inverse of f of x is x. They undo each other. That's a definition of what it means to be an inverse. We okay with that? I need nods of heads. Okay? Now, remember, we're trying to find what we want is an expression for the derivative of the inverse. This is, we're going to use g prime instead of this awkward derivative of the inverse of x notation. So we're trying to look at this and figure out what is g prime of x. So we're going to do a chain rule derivative. And what I'm going to do here you need to be able to do on your own. Because this, we'll talk about today, maybe tomorrow, how to do a derivative and inverse, but it might be weeks or months before we come back and it comes up again. And the formula we're going to come up here is not going to be, I don't want you to memorize it. I just want you to know how to do this, because you'll be able to recreate this even if you haven't looked at it in several weeks, I hope. Okay, so chain rule derivative, right? Derivative of the outside function, f prime, leave the inside function g of x alone, times the derivative of the inside function g prime. You with me? Need not depend. F prime of g of x times g prime of x. Derivative of x is 1. Now we're going to solve for g prime because that's the derivative of the inverse. G prime of x, going to divide all that over, is 1 over f prime of g of x. Okay? This is our holy grail right there. Okay? And we're going to recreate it, not memorize it, because it's just a couple steps. Start with what we know about a function and its inverse. You do a chain rule derivative, solve for g prime. There it is. Now, what this is saying is to find the derivative of an inverse at a point, you have to take 1 over f prime. There's the reciprocal of the derivative of the original function. This is the hard part, is figuring out what is g of x. That's f inverse of x. Remember, here we can find out what f inverse is, but on the one we're trying to do, we don't know how to figure out what f inverse is. It's okay. We're going to talk about in a moment how we can figure out what is f inverse at a particular value, even if we can't find f inverse of x, the function. That's coming, okay? Let's see if that works here. So we're saying if our original function was f, the x cubed function, this is saying that g prime evaluated at 8, that's the x value in our inverse, right? The derivative of the inverse evaluated at 8 is 1 over f prime of g of 8. You with me? So we have 1 over, well, the hard part is the g of 8. Well, we know how to do this because we said g of 8, the inverse evaluated, is 2. That's not always going to be so easy. So we're going to take 1 over f prime of 2. Finding f prime, that wasn't ever hard. We did that easy enough. We evaluated at 2, that was the 12, and sure enough, there is our 1/12 that we said it was. Okay, now, let's come back to our challenge. Okay, that's, I just wanted to do so that you could believe it. You see something where you actually know what that inverse is, and you can find the derivative of that inverse. Now, we're going to do it where everything is much more difficult. So, let's see, if we want the derivative of the inverse, we're going to call this g prime of 11. Okay, we're going to change the notation. Oh, okay, we need that formula. I forgot it. Oh, I remember how to get it. We know if g is our inverse, so f inverse of x we're going to call g of x, right? And we know that a function and its inverse have this property that f of g of x is equal to x. F of f inverse of x is equal to x. This we know. We can take this derivative, because we are the masters of the chain rule. The derivative of f of g of x is f prime of g of x, derivative of the outside function, leave the inside function alone, times g prime of x, the derivative of the inside function, and we know the derivative of x is 1. We'll solve for g prime of x by dividing that other stuff over. And there's our formula for the derivative of the inverse. Okay, you can do this. You can recreate it. We want the derivative evaluated at 11. We want g prime, the derivative of the inverse, at 11. So we have to evaluate 1 over f prime of g of 11. F prime, easy. We got that one already. G of 11, not so easy. What we mean by g of 11, remember, is we're trying to find f inverse of 11. But we don't have f inverse of x, the function. But we can work around it. Because if 11 is an x value for the inverse, that's the same as 11 being the y value of f. So we're going to put 11 as the y value for f, solve for that x, and that is our y value for the inverse. That's g of 11. Make sense? That's the hard part in all of this, always. So we're going to say 11 is x cubed plus x plus 1. Now we have two strategies here. We're going to use our calculator. This will be a calculator active problem. So we can either go y1 equals this, y2 equals that, and graph it. I think that's tougher because you may have to play, where's that going to happen? I think if you subtract the 11 to the other side, at least now you know we're just looking for where does it cross the x-axis. We may have to do a search in terms of x-min and x-max, but we're not worrying about what the y-min and the y-max are. Does that make sense? Okay, so let's do that. Okay, we're going to run to our calculator. We're going to put in x to the third plus x minus 10. All we really care is we're looking for where's across the x-axis. So for a window, I've got -5 to 5. I think that's going to be enough. I didn't think it too wild and crazy when I made this up. For a y-min and y-max, we can just go -1 to 1. All we're trying to do is see where does it cross the x-axis. Does that make sense? And I'm going to hit graph. Oh, this is a carefully constructed problem. It looks like it's exactly 2. Well, we could find that 0, or 2 cubed is 8, plus 2 is 10, minus 10 is 0. It is 2. You're welcome. So, x is 2, but we could find it on our calculator in general for some really messy decimal. Okay? Now, that is telling us that when x is 2, y is 11 on the function f, which means that for f inverse, it's the other way around. F inverse of 11 is 2. That's what we need right here. So this is saying now our derivative, g prime of 11, is 1 over f prime of 2. Well, the hard part's over. F prime is right here. That we did earlier, 3x squared plus 1. We plug in 2. 2 squared is 4, times 3 is 12, plus 1 is 13. There it is. There's our derivative of the inverse. At 11. We don't know what the inverse is. I can't write that down, but we can find the derivative of the inverse wherever we need to, with a little help from technology, perhaps. Make sense? Can't believe we got through that. You ready to try one? Well, of course, you say. Give me a problem like that. Okay, I will. Let's say f of x is equal to x cubed plus 2x minus 5. And we are challenged. 2x or 3x. How about 3x? Sorry. If I could read my own writing, this would be a lot easier. We're going to find the derivative of the inverse at 9. Want to try it on your own? You want to stumble through it together? Oh, that sounds like you want to try it on your own. Awesome. You only got 5 minutes, so hurry up. Figure out what X was? Hello, anybody out there? Very good. Which means G inverse of 9 is 2.
Could we do another one?
Let me, I only got 3 minutes. Let me do one where I'm going to give you the numerical values, because this is where you'll sometimes see it also on an AP question. Okay. Unlikely that this would be an AP question. More likely it's going to, not that it couldn't be, but more likely it's going to look a little different. Anybody not getting to 115? Okay, so let me start here. Okay, so let me give you a different twist on the same thing in 2 minutes or less. So you've got a table of values here, and we're going to have x, f of x, and f prime of x at a few known values. We're going to go -2, -1, 0, and 1. Oops. There's a way there. And the f of x values are going to go 3, 2, -1, 1, 3, 2, -1, 1. F prime is going to be -1, -2, 4, and -3. And so our challenge is, can we find f inverse prime of -1? So the hard part, how are you going to find out what is f inverse of 1? F inverse, right? That's what this means? Did I go too fast? We okay?
I think it's -1.
So you look down the F column where we have 1.
It's a negative.
Is it a negative? -1. Okay, have it your way. -1. And that's going to be 0. So that means this is 1 over f prime of 0. Does that make sense? And that we can read is 4. 1, 4.
Mr. Street, how'd you get 0?
So,
Parker Jackson